Hello everyone. Today here I'm going to talk about FLACS-Fire validation. This is my presentation, organization of my presentation. So I'll start with a brief introduction, and then I will go into jet-fire validation. In that I present different jet-fire validation cases, and then I will go into summary and future work. FLACS-Fire contain two major modules. One is the flow solver. Second, it's a fire specific solvers. The flow solver is very much similar to flux dispersion tool. The fire specific models contain eddy dissipation concept for combustion, and formation oxidation suit model. And for radiation there are two models available, one 6-flux model and discrete transfer model. 6-flux model can be used for quick and fast simulation. A discrete transfer model is very detailed one which can be used to model accurate radiative transfer in the fire scenarios. This picture shows the radiative transfer model in detail. As I mentioned, there are two different radiation transfer models are available. One is a discrete transfer model, another was a 6-flux model. Like both gives the radiative source term and radiative flux on surface. This radiative source term goes into enthalpy equation which solve for the temperature. Here we have done a detailed validation and verification campaign. The validation is primarily done to examine and quantify the predictive capabilities of FLACS-Fire. There are different levels of validation we have performed. First is a code verification, and then submodel validation, and integrated submodel validation, and then medium scale validation, and large scale industrial realistic scenarios. In this presentation we will discuss about jet-fire validation. Like my first jet-fire validation case is jet-fire in crosswind. In this case it's a small scale validation case where the methane used as a fuel, and velocity and mass flow rate and the nozzle diameter from the experimental data is given here. The release height from the ground is about 300 millimeter. The wind velocity is about 5 meter square per second. The FLACS-Fire used to model this case, and we have used about 100,000 grid cells. From the experiment there are two types of measurements are available. One is that temperature measurement at three different cross sections of the fire, and two, the radiometer measurements at different locations on the same level of the release. The FLACS-Fire simulations are performed. This slide shows that two-dimensional temperature distribution along the cross section of the release. Here the FLACS-Fire nicely predict the flame length. The experimental and the simulated flame length agrees very well. Next slide shows the comparison between the measured and simulated temperature profiles. As you can see, the agreement between these two are very good. FLACS-Fire able to capture very nice flow feature and temperature profile of this jet in the crosswind case. My next case is the my next diagram is the radiative heat flux plot. Here I compare the radiative transfer heat flux measured at the same level of the release in the symmetric plane as well as in the cross stream plane. The agreement between the measurement and the simulated simulation is very nice. Yeah, my next case is the large scale field experimental case. where the methane is used as a fuel, and it was released on the vertical direction at about 70 bar pressure. The leak diameter and the leak location and wind velocity, everything is given. Here the unknown is the mass flow rate. So I have used jet utility, flux jet utility to predict the pseudo source like the mass flow rate by varying the coefficient of drag. This picture shows the two-dimensional temperature distribution from the FLACS-Fire simulation. Here the flame length and the flame direction was predicted very nicely. My next picture shows that radiative heat flux impinging on the ground surface, where this radiative heat flux is predicted very nicely compared to temperature. My next slide shows on the cross section the distance from the leak and the incident radiative flux. Both here the FLACS-Fire and the experimental data is compared, both agreeing very nicely. So here the FLACS-Fire simulations are performed using mass flow rate estimated from jet utility, and the predictive capability of FLACS-Fire for the radiative flux is compared with the measurements. It agree very well. My next case is the SINTEF impinging jet case, where the propane used as a fuel, and it was injected towards the box-like target, where the dimension and the flow rate details are given here. They have measured temperature profile and heat flux close to target. So here we have done about 7-8 validation cases in this impinging jet with a different configuration. The details are given in the table. The competition details of this case is given here. The grid dimensions and the leak details, everything given here. Here we use jet utility to predict the pseudo source term, and here the discrete transfer method we used 256 rays to achieve converged heat flux distribution. This picture shows like flame impinging on the target and heat flux on the target surface. It's the same for the different cases. In this picture shows the contour plot of temperature and fuel concentration at the cross section. Here FLACS-Fire nicely capture the flow feature and the fuel concentration levels at the different locations. My next slide shows the radiation source term and absorption coefficient and soot volume fraction and so on. In my next slide I show the total radiative heat flux and total heat flux and convective heat flux. The prediction from this case is agreeing very well with the experimental data. This is for the another case where the cylinder placed in front of the target. Yeah, this table shows the validation of FLACS-Fire for different impinging jet cases. Here we have compared the maximum velocity temperature at maximum velocity location, and the total heat flux and the radiative heat flux. The FLACS-Fire predictions are agreeing very well with the experimental data within the acceptable range. There are some differences between the experimental and FLACS-Fire predictions. This is due to the experimental uncertainties, and turbulence radiation interaction is not considered in FLACS-Fire simulation, and the solid fuel heat interaction and conduction is not modeled, is due to also in our simulation we have used constant flow rate assumption. Conclusion from this impinging jet simulation is so we are able to predict the velocity distribution, temperature distribution, and maximum temperature and the radiative heat flux at target and at the monitor point. Also the total heat flux at the target and monitor point, very nicely. Here we have calculated the radiative heat flux at monitor point. Generally underestimate the measurement on the order of 10 to 15%, which is constant, which is very consistent with the neglect of turbulent radiation interaction and anticipated uncertainty of the prediction and measurements. My next case is the LNG flare, where I have compared the FLACS-Fire simulations against the experimental measurements. It's a large-scale turbulent natural gas diffusion flame, where the fuel used is a natural gas. This table shows the summary of the different cases. So I have chosen case number 5 to present here. So here the natural gas released on the vertical direction at the height of about 1.5 meter from the ground level, and the radiation heat flux is measured on about 5 different locations. The direction and the location of the radiometers are given here. FLACS-Fire simulations are performed. The details are given in this slide. This video shows the FLACS-Fire simulation of the flare case, which is presented here. Here the maximum temperature is predicted by FLACS-Fire is 1880, whereas the experimental measure is 1690. The flame height measured for this case is about 20 meter. FLACS-Fire predicts about 18 meter of flame height. The flame lift-off height is about 1.5 meter and between 1.5 meter and 2 meter from the experiment, whereas FLACS-Fire predicts about 2.4 meter flame lift. Also we have compared the radiative heat flux measurements and FLACS-Fire simulation. This shows FLACS-Fire predicted heat flux at a different monitor point. For monitor point 1 and 1, 3, 4, 5, there is a very good agreement between the experiment and the FLACS-Fire simulation. So the FLACS-Fire predicts structure of large scale natural air diffusion flame very nicely. And FLACS-Fire also predict the output quantities are predicted output quantities are temperature distribution, maximum temperature, flame height, lift-off, and radiative heat flux. My next case is LPG flash fire, where the LPG is released into the crosswind, and the effect of obstruction on the cloud development and subsequent ignition flame propagation and heat flux on the target are investigated. This experiment was performed at HSC. The released LPG is at an orifice plate with an 19 millimeter diameter, and the discharge height is about 1.5 meter above the ground. There are two cases considered in this study. One is without obstruction, second with obstruction. The details of the experiment is given here. These two cases are simulated using FLACS-Fire. The details of the competition domain and the grid size and the leak details are given here. In the experiment, they have measured the fuel concentration at different location and the radiative heat flux at a different location. So we have used a monitor point, series of monitor point to simulate these variables. Here, in the first case, C1, where there is no obstruction, this plot shows the concentration of propane after 144 seconds. These agree very well with this profile agree very well with the experimental investigation. And this is the case C2, where there is obstruction placed on the about 14 meter from the leak location. Here we can see the this obstruction blocks the is a propane from moving further downstream. This shows the flame propagation at each time step. So, for example, after ignition, the flame propagates towards the leak and moves upward due to the crosswind. This feature is very nicely captured by FLACS-Fire. This video shows the flame propagation, ignition and flame propagation for the case C1 where there is no obstruction. In this video, we can see the flame propagation for the case with obstruction. You can see the obstruction acts as a blockage for this dispersion as well as the fire scenario. So in this case, we have calculated the radiation heat dose at the monitor point location, different monitor point location. Using these values, we have segregated. We differentiated the region of first degree, second degree, and third degree burn zones. This can be used to map the zones where it's a safe or where it's not safe. Here FLACS-Fire captures the ignition and the flame propagation back to the gas source, and also the fire is very intense with the flame temperature exceeding about 1000 degrees centigrade, where the maximum flux range from 3 to 80 kilowatt per meter square depending on the test. The FLACS-Fire shows the effect of fence, which prevents a lot of gas flowing further downstream. The analysis of radiation dose at monitor point shows the personnel standing within the low flammability limit contour or the fatalities, while the outside is safe, will survive. Here the FLACS-Fire very nicely predict the distance of the low flammability limit and the flame speed compared to the experiment for the both case C1 and C2 with obstruction and without obstruction. My next case is the compartment fire cases, where I have considered two sub cases. One is a ventilation controlled case, another one is one is over ventilated case, another one is under ventilated case. In my over ventilated case, I have taken the famous Steckler experiment to validate FLACS-Fire. Here the commercial grade methane used as a fuel, and the gas burner is a circular and it's 0.3 millimeter diameter. The heat release rate is 62.9 kilowatt, and other details about the geometry and the burner are given here. Here they have measured temperature as well as velocities at the doorway. This plot shows the comparison between temperature at the corner of the room measured and FLACS-Fire simulated. In FLACS-Fire simulation, we have done two cases, one without radiation and with radiation. With radiation, the agreement between the FLACS-Fire and the experiment is very good. My next slide shows the velocity profile at the doorway, where we compare FLACS-Fire and experimental measured velocities. From this picture we can see the cloud height, smoke layer height predicted from both experiment and FLACS-Fire. The agreement between these two are very good. My next case is the underventilated compartment fire case, where I have considered the SINTEF propane jet, where the fuel used is a propane, and the gas burner diameter is 25 millimeter. The flow rate and the room size and the details of measurements are given here in the picture. The number of grid here used is about 52,000 cells. This video shows that temperature profile inside the room and outside the room, as well as the CO2 and the oxygen content, additive flux and the CO2 content inside the room. You can see from this video that initially the fire starts as a over ventilated case. Once the room filled with the smoke due to lack of oxygen, the fuel goes along with the air and it burns out, straight outside the room. This picture shows the comparison of velocity profile for the SINTEF enclosure case. Here we have compared the FLACS-Fire and experimental measured velocity profile. The smoke layer height even for this case is predicted very nicely by FLACS-Fire. The comparison between the temperature profile and from the experimental measurement as well as the FLACS-Fire simulation is shown here. Generally the agreement is an acceptable limit. That the temperature counter with and without radiation is shown here. FLACS-Fire also predict the high temperature region, which is close to the mass fraction of 0.06. In this case very nicely. This slide shows the concentration of CO2 at the cross section of the compartment, where there is experimental measurement close to the doorways about 14% of CO2. FLACS-Fire predicts about 17% of CO2. The concentration of oxygen also predicted using FLACS-Fire. The experimental measure is about 0.9 percentage. FLACS-Fire predicts 0.8. Also, we have predicted soot mass fraction. The heat flux on the ceiling is shown here. The SIDF experiment, they have measured the heat flux at different locations. So we have compared FLACS-Fire prediction against those experimental measurements. The agreement between these two are generally very nice. The heat flux on the west wall, similarly the heat flux and total heat flux on the west wall also shown here. For the total heat flux and the radiative heat flux, the agreement between the FLACS-Fire and the experiment data are very nice. So FLACS-Fire predicts the correct trend of velocity, temperature, and species and soot concentrations for the over and under ventilated cases. Also here we have demonstrated the importance of the radiative heat exchange. The predicted radiative and total flux on compartment roof west wall using DTM model. So we have used DTM to predict the heat flux. My next case is a solid flame approximation, application of FLACS-Fire for solid flame approximation. Solid flame models are used for the screening studies. For example, in case of pool fire, you want to know the heat flux, different heat flux zones. So you can use FLACS-Fire. Here we have assumed the fire as a solid object with well defined dimensions with given surface emissive power. So it's a simple version used for describing the thermal radiation from large hydrocarbon fire. The fire is modeled as a solid body of simple geometrical shape whose surface emit radiation at a specified constant rate. The solid flame model assumes the flame to be a cylinder with a diameter equal to the base diameter of the fire. The flame height equal to length of visible flame plumb. Generally the radiative heat flux is a very important parameter which we are looking from the fire simulation. So if we are able to predict that heat flux from very quick simple solution, then it's really very good parameter for the further analysis. In my first case, I have taken the pool fire with a 10-meter base diameter. Here the target is placed at about 25 meter from the axis of the fire. The surface emissive power from this fire is assumed to be 150 kilowatt per meter square. This can be calculated from the well validated correlations available in the literature. The assumptions are soot formation not obscure the first 10 meter of the flames, and there is no flame tilt, which means it is a wind free condition. So I have used a theoretical radiative transfer calculation to calculate the heat flux received at the target. Also I have used FLACS-Fire where I use a discrete transfer method to calculate the heat flux at the surrounding of the fire. So here the both coupled property and uncoupled property versions are used. Here you can see the heat flux predicted at a different height on the target can be simulated. My next case is a solid flame model is a fireball, where I used the dynamic fireball correlations to achieve the fireball sizes and surface emissive power. This information I used inside FLACS-Fire to calculate the radiative flux at a different location at the for the fireball at the maximum diameter. Here the experimental value is about 90 kilowatt per meter square, and the FLACS-Fire prediction is about 100 kilowatt per meter square. This picture shows the capability of FLACS-Fire for to predict the three-dimensional radiative flux. If you use a simple method or simple tool to model the radiative flux, where you cannot model three-dimensional geometrical shapes, in FLACS-Fire discrete transfer method you can use three-dimensional model. And here we use the ray trace method, so there is independent of geometrical complexity. So in future we are planning to do the export option for this solid flame model, where you do the FLACS-Fire simulation using full CFD simulation, and then export your flame dimension to the solid flame model, and then do the quick screening study by varying different fire location at different locations on the platform. So this diagram, this picture shows the validation summary of FLACS-Fire. So we have done the validation for different submodules like radiation, flow turbulence, soot combustion, and pseudo source models, and pool evaporation model, and so on. So also here we have done the validation for jet fire, for various jet fire scenarios like simple open jet fire, confined jet fire, impinging jet fire, and flash jet fire, and so on. Also pool fire and solid flame model. So with this FLACS-Fire, one can simulate a jet fire in open, jet fire in class in crosswind, and impinging jet fire, jet release with a delayed ignition, and compartment fires with a different fuel, and so on. Like what are the outputs are reliable? Flame shape, flame length, gas temperature, mixture fraction, flame propagation, flow, species, radiative heat flux, total heat flux, and heat dose, and so on. These are the like output are reliable from FLACS-Fire. So there are two main category of fire effort can be simulated from FLACS-Fire. One is a thermal effect, second is a toxic effects. This table shows the available output parameter for the three-dimensional as well as monitor point and surface from the simulation. This table shows the different applications of FLACS-Fire for different jet fires and pool fire and solid flame models. Here this table shows the development and GUI support and validation and large validation cases. This is the future plan, where we are planning to like parallelize the FLACS-Fire solver. Thank you. That's all.